since the very first version of Mathematica, we had a command called Noncommutative Multiply, which was really a placeholder that did nothing, that allowed you to add your own rules. Well, we've now built out non-commutative algebras. So these things come up in all kinds of theoretical subjects. So in things like quantum mechanics and in kind of geometry calculations. So these are algebras where A times B is not the same thing as B times A. And we can treat that very generically and say just everything is non-commutative. But in this case, I'm doing a slightly more interesting algebra. I'm setting up an algebra where everything is non-commutative except for the symbol C, which does commute with other variables, and S, which is a scalar. Every other symbol is going to be treated as non-commutative. And now I can say, take this expression as a new, there's a new special character for non-commutative multiply, but I can type star star like I could in the first version of Mathematica as well. And I'm saying expand that operation respecting the rules of commutativity and non-commutativity that I've declared in the algebra. And here's the expression. And you can see there's a range of algebraic operations like Grosvenor basis and simplification and you know, generalized versions of power that can operate on these kinds of algebras. So a whole new area of algebra. It's a pretty big deal if that's your bag. We've also built out really some of the just small missing low, you know, special operations within matrices. Obviously, we've been doing matrices for a long time, and really you've been able to do all of these things yourself. But hey, why should you? So there is a whole set of new standard operations that are doing different kinds of decompositions, different kinds of polynomial representations, projections on matrices, all things that you could probably do in at most half a dozen lines of Mathematica, but they now have their own name functions. And these are all very standard operations that now just work out of the box. We've had integral transforms for a long time. I think there's about 4 main kinds of integral transform, and we've had 3 of those supported for quite a while. Things like Fourier transform being a very popular one, and Laplace transforms being another. And I'm trying to remember the 4th one, but the one we've been missing for a while is Hilbert transforms. These come up particularly in things like signal processing, of handling imaginary and complex parts of signal systems. And this is a pretty full, because it sits on top of integration, which of course is supremely powerful in Wolfram language. Then we can now basically do essentially most Hilbert transforms that you might expect to be solvable are done now in a single step with this new Hilbert transform operation. Another space we're filling out, or just about to finish filling out, is special functions. We already have by far the biggest collection of special mathematical functions, and we are kind of running out of special functions that exist that we haven't got in the Wolfram language. One of the last to be added is Lommel functions. These things come up in things like diffraction patterns and optics problems. So like every other special function, we have a full implementation. So that includes real numbers, high precision arithmetic. It includes exact arithmetic where those things are known, and it includes things like complex number arithmetic, again, and complex number arithmetic at arbitrary precision. So I should have pre-evaluated this one. It actually takes a little while to compute, but in a moment we're going to get a complex 3D plot of the real and imaginary parts of that function over the rectangle from plus or minus 3i and 3 in the real domain.